Hello everyone, welcome to the Audio Precision webinar. Today we'll be discussing hearing aid audio test. Joe Bajin will be leading the conversation and providing demonstrations in APX 500 software. My name is Paige, and as the producer of the event, I would like to go over a couple housekeeping items before we get started. So first, please note that this session is being recorded. Oh, I'm sorry, a technical difficulty. Hold on. I apologize, everyone. Sorry, I had a technical glitch on my end, but I think I've got it remedied. So again, this session is being recorded, and a recording of the session will be shared with you via email. So be looking for a link in your email to review this session. Secondly, we welcome questions during the webinar. So if you have a question for Joe, please submit it via the chat function in Microsoft Teams, and we will answer those as we go throughout the event. Now, Joe has a lot of info to share with you today, so without further ado, Joe, I turn it over to you.
All right, thank you, Paige, and thank you everyone for attending the webinar today. I wanted to start out just by pointing out that I have two logos on the screen here, Audio Precision and Grass Sound and Vibration. And as many of you probably know, we're now part of the same company, and we've actually merged our support and sales and marketing efforts. So I'm part of the support group. We have a support team here in the United States. We also have a team in Europe, in the United Kingdom, and also in China. All right, so we have a lot of material to cover today. I'll just launch right into it. The agenda we're going to follow here is first, a very brief introduction of an overview of hearing aids. So I just want to be the first to say that I have a lot of expertise in audio analyzers, but very little expertise in hearing aids. So I'm by no means an expert, and if that's what you're expecting, I'm sorry, but you may be disappointed. Next on the agenda, we're going to cover the ANSI and IEC standards for hearing aid test. We'll also review the test requirements in those standards in some detail. We'll have a talk about the test equipment needs for conducting these tests. We're going to do a demonstration of the major tests required in the two standards, and then we'll have time for some questions at the end of the presentation if we haven't answered them during the presentation. All right, so a little bit about hearing aids. These are very complex audio devices, and they're quite interesting from an audio test point of view. Now, they're one of the few audio devices that are both acoustic in and acoustic out, which makes them quite unique. They're tiny little devices that are battery powered. They fit in a small package, typically behind someone's outer ear, or they can even be hidden right inside the ear. They have a couple of microphones typically. They have a power amplifier, a loudspeaker, and a digital signal processor built in, and then some controls. Now, those are the basic elements of a hearing aid. In addition to that, there are a lot of optional features that are available on these devices. These include things like noise reduction. They can have directional microphones, so the user can detect the direction that a sound is coming from. They can have a telecoil, which is a means for picking up a magnetic field so that the audio can be transmitted from passing current through a coil rather than over the air for use with telephones and also in some spaces like churches, for example, when they're equipped with a telecoil loop. They can have wireless connectivity. Now, there are many hearing aids that support Bluetooth, and this is becoming increasingly important, especially with a new standard that the Bluetooth SIG has just developed for hearing aids. They can have remote controls, so you can control the hearing aid from an app on your smartphone, for example. They can, some of them have direct audio input, so a little small analog input that you can connect a different device directly to the hearing aid. They can have variable programming where the program changes according to the circumstance that the user is subjected to. And finally, they can have synchronization. So if you have a left side hearing aid and a right side hearing aid, there can be communication between the two hearing aids, the left and right side, to optimize the listening experience for the user. Some of the styles of hearing aid. So one of the main ones that we're familiar with is the behind the ear hearing aid here on the left. So this has the body of the device that sits behind the outer pinna. It has a hook that fits over the ear, and typically there's a plastic tube that's attached to the end of the hook and conveys the sound into an ear mold that's placed inside the ear cavity. A smaller version of this is the mini behind the ear. It's slightly smaller in size with perhaps not as many features. Another variant of this is the receiver in the canal. So with this device, the main behind the ear ones have the receiver. It's called a receiver. It's actually a loudspeaker. Also in telephones, for example, we call the earpiece a receiver. And in these devices, the receiver is in the body of the hearing aid, and in the receiver in the canal, the receiver or loudspeaker is inside the ear canal, and the sound is conducted via wires from the power amplifier rather than from via a plastic tube. Another type is the in the ear or ITE hearing aid. So this is a larger unit that sits in the outer ear. There's also a smaller version of this that sits further down inside the ear canal called ITC or in the canal. There's a tinier one yet called completely in the canal, which sits further in the ear canal. And finally, an invisible in the canal. And this is so small that it's inserted inside the ear canal and completely invisible from the outside. Now we'll look at some of the hearing aid test standards. One of the main ones is the ANSI, American National Standards Institute and Acoustical Society of America S3.22. This was revised in 2014 and reaffirmed in 2020, and the title is Specification of Hearing Aid Characteristics. So this is the standard that is used for typically for production test of hearing aids. Very similar standard is the international version IEC 60118 Part 7. So 60118 is quite a large family of standards that pertain to hearing aids, and Part 7 is for measurement of the performance characteristics of hearing aids for production, supply, and delivery quality assurance purposes. And this is very similar to the ANSI standard. They're virtually identical except for a couple of minor differences. Another IEC standard in that same group is IEC 6011 Part 0. It's simply called Measurement of the Performance Characteristics of Hearing Aids. This has a lot of the same tests, but it's the kind of standard you would use if you're qualifying a hearing aid as a new product and you want to produce a data sheet. So there are further tests. It covers a wider frequency range, for example, and there are some extra tests required in that standard. Now, some of the measurements we're going to cover today, I'll go through these in detail in the subsequent slides, but I'm just going to mention them for now. So we have the OSPL 90 frequency response, the full-on gain frequency response, the basic frequency response, total harmonic distortion, equivalent input noise, the battery current, the steady-state input-output, attack and release, intermodulation distortion, and the SPL-IV curve. And as I mentioned, I'll explain all of these in subsequent slides. So first, the OSPL 90. This stands for the output sound pressure level for an input of 90 dBSPL. So we're going to measure the sound pressure level in the coupler connected to the hearing aid with a microphone at an input level of 90 dBSPL, with the gain of the hearing aid set to full-on gain or maximum volume. And the frequency range is typically 200 hertz to 5 kilohertz for the production test standards, and it would extend out to 8 kilohertz for the Part 0 IEC 60118 Part 0 standard. Now the results here are the OSPL 90 curve, which might look something like this. Another metric that we want is the maximum OSPL 90. So we look at this curve and we essentially pick off the maximum value here at the peak and record that. And another metric is called the HFA OSPL 90. So HFA stands for high frequency average. And the way that's computed is we take three frequencies, 1 kilohertz, 1.6 kilohertz, and 2.5 kilohertz. We calculate the average of the levels or the gain at those three frequencies, and that's called the high frequency average, or HFA. The next measurement we'll take is the full-on gain measurement, or FOG50. So here again, we measure the sound pressure level in the coupler. The input level in this case is 50 dBSPL. The gain is at full-on gain, the same frequency range, and here we're measuring a gain curve like the one on the right, and we'll also compute the high frequency average full-on gain, which again, we average the values at 1K, 1.6, and 2.5 kilohertz. Now, another important metric is the reference test setting, and for this we measure the HFA gain, so that's the gain at the three HFA frequencies of 1, 1.6, and 2.5K. The input level in this case is 60 dBSPL, and what we need to do is adjust the gain until the HFA gain that we measure is equal to the HFA OSPL 90 minus 77 dB. So the result is called the reference test setting, and the gain at this reference test setting is called the reference test gain. Now, for analog hearing aids, you have to find this, this point by trial and error, essentially, by adjusting the volume knob of the hearing aid. But for modern digital hearing aids, this is set programmatically. So for a digital hearing aid, there's a programmer connected to the hearing aid during the test, and you just send it a command to set the gain at reference test setting. Another measurement we'll be doing is the frequency response. So here, again, we're measuring the sound pressure level in the coupler. The input level in this case is 50 dBSPL. The gain is at the reference test setting. We have the same frequency ranges as before. And here we're measuring the frequency response curve. We want the HFA, the high frequency average, and we want the frequency range. Now, to compute the frequency range, what we do is we draw a horizontal line at the HFA level of this curve. We draw a parallel line at 20 dB lower than the curve, and we find the points F1 and F2 that intersect the curve at that line. And that is the frequency range of the hearing aid specified, F1 to F2. Now, for the basic frequency curve, the ANSI and IEC standard call out this tolerance method for the frequency response curve. And this is a set of limits that are based on the model curve or a curve for the specified model. So you provide a curve for the model and you construct the limits from that curve. And how you do that is you split the frequency into two ranges, the low band here and the high band. So the low band extends from 1.25 times F1, or 200 hertz, whichever is higher, up to 2 kilohertz. And the limits in that range are plus or minus 4 dB, so you can see them here on the graph. The high band extends from 2 kilohertz to 4 kilohertz, or 0.8 times frequency F2, whichever is lower. And in this case, the limits are plus or minus 6 dB. So you can see that we get a step change here at 2 kilohertz from limits of plus or minus 4 dB to limits of plus or minus 6 dB. Now, the way the standards are written, these limits are drawn on a transparent overlay, and you lay this overlay on top of the graph, and you're allowed to shift it vertically so that the curve is centered, the measured curve is centered within the limits, but you're also allowed to shift it horizontally in frequency, up or down in frequency by up to 10% to allow the curve to fit in the limits. Now, of course, today, these days, these standards were written many years ago when people used transparencies. No one uses transparencies today, and this is all done via software. And I wanted to point out that we've added a new derived result to the APX software called the ANSI S3.22 Fit Limits to Data. And I'll be showing that later in the demonstration. Now, for harmonic distortion, we measure the sound pressure level in the coupler with the gain of the hearing aid at the reference test setting. And we have a series of 3 or 4 frequencies and a different level at some frequencies. So at 500 hertz, we have an input level of 70 dBSPL. At 800 hertz, also 70 dBSPL. At 1.6 kilohertz, 65 dBSPL, and at 3.2K, 60 dBSPL. And the result here is just the total harmonic distortion in percent. The equivalent input noise is another important metric. So here, there's no input. There's no signal being generated acoustically into the hearing aid. We're just measuring a quantity L0, which is the noise in the coupler. The gain of the hearing aid is set to the reference test setting, and the frequency that we're measuring over is bandwidth limited from 200 hertz to 5 kilohertz. And then we calculate the equivalent input noise, which is equal to the measured level in the coupler minus the HFA gain at 50 dB input at SPL. The battery current is another important metric. So these devices are all battery powered, and of course it's important to know how much current is drawn by drawn from the battery to the hearing aid for typical use. So for this test, we have an input level of 65 dBSPL. The gain of the hearing aid is at the reference test setting. The signal is at a frequency of 1 kilohertz, and we just want to measure the battery current. The steady state input output is a measurement for hearing aids that have automatic gain control. So in this case, we're measuring the sound pressure level in the coupler. The input to the device is a sine level at a frequency of one of these values, 250, 500, 1 kilohertz, 2 kilohertz, or 4 kilohertz. The gain of the device is set to the reference test setting. And in this case, we sweep the level of the sine wave from 50 to 90 dBSPL in 5 dB steps. And the result is this input-output curve. So you can see in this example, the hearing aid is quite linear from 50 to about 57 dB, and then it starts to roll off. And that's where the automatic gain control is kicking in. Another measurement for hearing aids with automatic gain control is called attack and release. So here we're measuring the sound pressure level in the coupler again with the gain at the reference test setting. The frequency can be any one of these 4 frequencies, 250, 500, 1K, or 2 kilohertz. And here what we do is we abruptly increase the level from 55 dBSPL to 90 dBSPL. And we measure the amount of time that it takes the hearing aid to settle within plus or minus 3 dB of the final setting. That's called the attack time. For the release time, we do the opposite. We decrease the level abruptly from 90 dBSPL down to 55, and we measure the amount of time that it takes the envelope of the hearing aid response to settle within plus or minus 4 dB of the final level. Another measurement called out in the standards is difference frequency distortion. So ANSI calls it difference frequency distortion, and we'll see that the IEC, it has a slightly different label, but it's basically the same thing. So here again, we measure the sound pressure level in the coupler with the gain at RTS. We use a dual sine signal, so there are 2 sines of equal amplitude at frequencies that are spaced 125 hertz apart. And for the ANSI version, F1 is higher than F2, but the difference is 125 hertz. And we compute these distortion products at frequencies F1 minus F2, 2F1 minus F2, and 2F2 minus F1. And we record the difference frequency distortion versus frequency, as shown on the right here. So as I've shown in this graphic, we have a measurement that we've just added to the APX software called ANSI S3.22 IMD frequency sweep, and it's meant to do this measurement exactly. Now in the IEC standard, it's called intermodulation distortion, but it's basically the same measurement. You have 2 sine levels at a slightly different amplitude, different by 1 dB, essentially. Here you have the same difference frequency. Something that's different in this standard is that F2 is the higher of the 2 frequencies, but really the differences are the same, 125 hertz. And in this one, you only compute 2 of those 3 distortion products, F2 minus F1 and 2F1 minus F2. And then a difference is you plot the total difference frequency distortion versus frequency F2. And just like the ANSI test, we have a special measurement in the APX software that we've just added called the IEC 60118-0 IMD frequency sweep. Now the SPL-IV is for hearing aids that have a telecoil that responds to a magnetic field. So in this case, we're also measuring the sound pressure level in the coupler with the gain of the device at the reference test setting. But rather than an acoustic signal, we put the hearing aid in telecoil mode, and we generate a loop current within the loop of the hearing aid test box at a level of 31.6 milliamps per meter. Now, the amount of current depends on the length of the loop, and for the test box that I will be using today, it's I'm going to show it a little bit later. It's called a TBS-25, but it has a loop length that requires a current of 7.9 milliamps. And we sweep that sine signal from 200 hertz to 8 kilohertz. And for this measurement especially, we use a measurement in APX called the bandpass frequency sweep. So the telecoil tends to be very noisy, and this measurement uses a very, very narrow bandpass filter. We call it a window width filter. It's implemented via Fourier transform analysis, and it's as narrow as a bandpass filter can be. And the result that we record is the bandpass level versus frequency as shown in this graph. All right, so let's talk a little bit about the equipment required for doing these tests. First of all, we need an acoustic test chamber. We also need a measurement microphone. It's very important. We need a 2cc coupler. So this is defined by similar standards, or standards that are part of the same standards on hearing aids. They define this 2cc coupler that the hearing aid connects to, and the microphone is inserted in the coupler. I have some pictures in subsequent slides. It's very good to have a sound level calibrator, and what this does is it generates a known sound level, and you can use it to set the sensitivity of the microphone within the software of the audio analyzer. We also need a dummy microphone, and I'll explain what that is in an upcoming slide. Finally, we need an audio analyzer, and some additional accessories that are required are a power amplifier to power the loudspeaker, a power amplifier to drive the telecoil loop of the test box for the telecoil tests, a microphone power module for signal conditioning of the measurement microphone, and a battery simulator to power the hearing aid and to measure the battery current. Now, I've colored all of these devices the same color as the audio analyzer, and that's because in the measurements that I'll be doing today, I'll be using our APX 511 audio analyzer that has all of these accessories built into it directly. All right, so for the test box, one of the most popular test boxes in use is the Interacoustics TBS-25 sound test chamber. This is a small chamber that fits on a desktop, really. It provides about 45 dB of noise isolation, which is nice to separate the test from the noise in the environment. It's specified to be anechoic at frequencies that are 500 hertz and higher. It has a built-in loudspeaker shown here with a very smooth response from about 50 hertz to 80 kilohertz. It has a built-in loop for telecoil measurements. And then for convenience, it has a patch panel on the inside that you can connect things to, and a mating patch panel on the outside to bring the signals out to the audio analyzer. I just wanted to point out here that the working surface is quite small. The area of that surface is less than 6 by 6 inches or 15 by 15 centimeters. Not very much room to work in, but luckily hearing aids are quite small and they fit well in the test space. Now we also need a measurement microphone that goes inside the coupler, and our sister company Grass has a lot of choices when it comes to microphones. Now for this application, we want a microphone with a pressure response, and Grass has several that foot the bill. One of the most common ones that would typically be used for this application is called the Type 40AO, half-inch pressure cap, and it has a nominal sensitivity of 12.5 millivolts per Pascal. Now, for use with this capsule, you need a preamplifier, And Grass has a very nice short preamplifier for this application. Now, the two are shown in this picture to the right here. This is the preamplifier and the pressure capsule combined. And as you can see, the total length of the two combined is about 37 millimeters from tip to tip. So that's really important when you have such a small working space in the acoustic test chamber. This is available from Grass. Rather than buying separate components, you can buy it as a system called the 46A-S2. And that's provided as a system, and it's programmed with TEDs. And you can also get the S3 version, which has a right angle adapter built in. I don't have a photo of that, but it's shown in the picture here. You can see the preamplifier, the right angle adapter, and then the pressure capsule on top of the right angle adapter. And this will orient the capsule at 90 degrees to the cable, which can help you save some space in service. All right, we also need a and these are sketches of the setup from the ANSI S3.22 standard. So you can see for testing an ear hearing aid, you would have this configuration, which has an opening to the body of the device, and there's sealant material used to place the device into the coupler. And then for a behind the ear hearing aid, we have this H8-2 configuration. And in this case, you would use a tube to connect the ear hook of the hearing aid into the body of the coupler. Now for this application, Grass provides this RA0038 2cc coupler for a 1/2-inch microphone. And you can see you have the parts here to configure it for the HA2 type, or you can change the configuration and turn it into the HA1 type. So you have the ability to do both in the ear and behind the ear hearing aids with the one coupler, which is a nice feature. Now, in addition to these basic accessories for hearing aid test, Grass has quite a number of products that are useful for hearing aid test. For example, shown here is the 0.4 cc high frequency coupler. So this can be used to test up to higher frequencies, and this is especially useful for testing hearing aids for children. I believe it's about to be incorporated into international standards in the future for hearing aids for children. They also have here a 2cc coupler for a 1-inch microphone, and they have a variety of ear simulators, sometimes called 711 couplers, or the current standard governing those is IEC 60318-4. And Grass has a standard ear simulator, a high frequency ear simulator, and a high resolution ear simulator. And of course, Grass has a variety of cables for connecting the microphones to the audio analyzer. Now, I mentioned it's important to have a sound level calibrator, and this is useful for setting the sensitivity of the microphone in the audio analyzer software. It's also very useful to check the connectivity between the microphone and the analyzer. We're measuring very small voltages with microphones typically, and with a calibrator, you can check that you have good connectivity as well as setting the sensitivity. Now, this is one of the nicest calibrators that I've ever used. As you can see, it has a digital display. And nice thing about it is it has 2 different sine frequencies. You can generate either 250 hertz or 1 kilohertz. And the 250 hertz is especially important because that can be used to calibrate ear simulators directly. It also has 2 sound levels. You can set it for either 94 or 114 dBSBL. It has a built-in feedback microphone so that it can compensate for variations in atmospheric pressure. And it has this nice digital display which can show the sound pressure level and the frequency, as well as the temperature, the barometric pressure, and the relative humidity. Now, I promised that I would explain the purpose of the dummy microphone. And the dummy microphone is really just a small piece of metal, essentially, that's the same approximate physical size as the reference microphone. And the reason for this, there are 2 ways of conducting these tests. You can either use 2 microphones. So you would have 1 microphone inserted in the coupler, and another reference microphone at the test point to measure the sound level, and you can use that to regulate the sound level. But that requires 2 microphones, and it also requires an audio analyzer with 2 channels. Now, we would be happy to sell you twice as many microphones and analyzers with 2 input channels, but you can actually do the test with a single microphone by using this dummy microphone and swapping the position of the 2. So when we're setting the level of the sound field inside the chamber and equalizing the speaker, we put the microphone at the test point, center of this blue circle in front of the speaker, and we put the dummy microphone inside the coupler. Then when we're ready to do the hearing aid measurements, we flip the position of these, and we put the dummy microphone at the test point and the reference microphone in the chamber. And this kind of keeps the sound level at the same level, because as you can imagine, it's a very small test space, and it's important to control the sound field so that we get an accurate setting of the sound. So that's the reason for the dummy microphone, excuse me. Now, this is the APX 511B hearing instrument analyzer. I'm using this analyzer today to conduct the demonstration. This is a specialized model for hearing instrument test. It includes a power amplifier to drive the loudspeaker, a power amplifier for the telecoil or loop, a battery simulator to power the hearing aid and to measure the battery current, and then a CP power for the measurement microphone. This runs the same APX software as our analyzers for research and development, and so with this we can have easy test development between engineering and production. It has fast measurements and it has high performance, as well as very flexible software. Now the 511 is a little different from most audio precision analyzers because it has no connectors on the front panel. It just has a series of LEDs that power if the speaker is being driven, the telecoil is being driven, the battery, or the microphone bias power is on. On the rear panel, we have a standard BNC connector for the microphone, and then we have this 15-pin D-sub connector, which carries the signals for the speaker, in the box, the telecoil loop, and the battery simulator. We also provide this breakout cable with the analyzer. So this photo here at the bottom shows the back of the TBS 25 sound test chamber patch panel. And you can see the most important ones are the loudspeaker connections here. These are pin jacks like you would have on a consumer loudspeaker. And we have this cable with the DB15 at one end. We have the speaker pin jacks at the other end, the 6mm phone plug for the loop, which goes over, and a 3.5mm plug for the battery adapter that goes over here. So it's very easy to connect the chamber to the analyzer, connect the microphone to the analyzer. Now, I should mention that what I'm going to show you today requires some APX software. So these are extra software features that don't ship with the product, but they can be downloaded from our website. So first we have the hearing aid test plugin. This adds several derived results that are used in the hearing aid test project. We have the attack and release plugin. It adds attack and release measurements per ANSI S3.22 and IC 60118 Part 0. And then optionally, we have an octave analysis plugin that adds fractional octave analysis in case you want to do those measurements. Those aren't required by the standard, but I think I have one built into the project file we're going to do today. And as I mentioned, these are free downloads at ap.com, our website. So let's go ahead and do the demonstration. So today, I just wanted to mention, I'm basically following what's laid out in this tech note number 133. And this is a tech that describes the tests that we're doing in more detail. Download it and read it at your leisure. And we also provide a series of project files for the APX 511 as well as other audio analyzers in our platform. And today I'm using the TBS25 test box that I have here on the bench. I will be using a little, an older analog hearing aid. And the reason I'm doing that is that I don't have to program it. It just has one program that it came with. And I don't have to worry about connecting a programmer and being able to download firmware into a digital hearing aid. So that's the device that I'll be testing today. So I'm just going to break out of the presentation here. And I want to bring up the APX software. And this is currently connected to the APX 511. Now, this is the state of the software. When you first load it, it has an empty project file, essentially, with one signal path in it. And just point out a couple of things that are a little bit different about the APX 511. This is their speaker, telecoil, and none. And on the input side, the connector choices are microphone, battery voltage, battery current, speaker voltage, telecoil current, microphone bias voltage, and we can do file analysis. So typically here you would want to test with the microphone. If you turn on the mic bias voltage, that essentially turns on the CCP power. You can see I'm getting a signal here in the FFT monitor that's responding to my voice, essentially. And I can just kick on the generator if I open the verify connections. And at this point, nothing is calibrated, but we'll just see that we can generate a signal, measure something, and I get a sharp sine wave in the FFT monitor. So rather than spend a lot of time configuring the project, what I'm going to do is just load a test project that I've created for this purpose. And this is the one that you can download with the tech note that I described earlier. So if we look at recent projects, I'll load the project here, and we'll just run through some of these basic hearing aid measurements. So this project file has several signal paths in it. I have signal path 1, which is called chamber, signal path 2, measurements. And you'll notice that there are different measurements in here with checkboxes checked. And some of them are checked and some of them aren't. And what I have here is 2 different sequences. So I have and another sequence called test DUT, or test device under test. And really a sequence is just a different collection of checked boxes. So let's look at the calibrate sequence, and let's just run that sequence, and it does. So I'll click the run sequence button. After choosing the calibrate sequence, I get a prompt to insert the microphone in the calibrator, set the calibrator level to 94 dB, and turn it on. So I'm just going to follow the directions on the prompt here. The mic is inserted in the calibrator. I'll turn it on, and you can see a nice sharp peak here at 1 kilohertz. And in the prompt here, I'm measuring the level. It's 94.025. So I calibrated it earlier today, but it's drifted a insignificant amount. And the sensitivity is at 11.8 millivolts per Pascal. And I'm currently measuring 94.03. So when I click OK, it's going to adjust that sensitivity a little bit and dismiss the prompt. And now you can see that it's showing closer to 94.0 dB. Next, I get a prompt to place the hearing instrument at the test point and the microphone at the leveling position, or the test point, and to ensure that the hearing aid is switched off. So I put the microphone at the test point and the hearing aid as shown. I'll close the box and click OK to dismiss the prompt. So what the system is going to do now is regulate the speaker to a sound pressure level of 80 dB SPL. Then I'm going to measure the frequency response of the loudspeaker without any EQ, as shown here. I'm then going to invert that EQ, invert that curve and apply it as an EQ. and I end up with the leveled response of the loudspeaker. So as shown here, my generator is set to 90 dBSPL, and if I look at the RMS level versus frequency, you can see that it's a pretty flat response. And I've also shown the relative level here with limits, so plus or minus 1.5 dB up to 3 kilohertz, and plus or minus 2.5 above that. And we have a result here that shows the deviation from flatness, and you can see it's plus or minus 0.282 dB from 100 hertz to 8 kilohertz. So essentially, I've calibrated the microphone, I've calibrated the output of the speaker at 1 kilohertz, and then I've leveled the output of the speaker to make it flat, and I have a calibrated output at all frequencies from 100 hertz to 8 kilohertz as required by the standard. Next, we'll pick the test device under test sequence. And if I hit the run sequence button, the system will run through the hearing aid tests. So first I have a prompt to enter the device ID. This could be the model number or the serial number of the device. And as shown, there's a barcode here in the picture. I could use a barcode scanner. I don't have one hooked up, so I'm just going to enter a number 1, 2, 3, 4, 7, 8. And first the system is going to measure the ambient noise in the box. Then the 1/3 octave noise. Now we're measuring the frequency response at the test point. Okay, I get a prompt to connect the battery simulator to the hearing instrument or install the battery. So the battery simulator is already connected. I'm going to click OK. And I get a prompt to switch the position of the dummy microphone to the test point and the reference microphone to the coupler. So I've inserted the mic in the coupler. I have the dummy mic at the test point. And the prompt also says, ensure that the hearing instrument is switched to acoustic mode. So I'll turn it on and I'll set the gain at full on gain or maximum volume. And now close the chamber and click the OK to dismiss the prompt and carry on. So here's the OSPL 90 frequency response, the full-on gain curve. Here we're using that bandpass frequency sweep with a very narrow window width filter. And we're stepping through the ISO R series, R40 series, or 1/12th octave. Here we have the basic frequency response curve. So I have a prompt to set the hearing instrument to the reference test setting. Now, in this case, because it's an analog hearing aid, I've just made a little mark on the volume control, and I'm just going to rotate the volume control to the approximate reference test setting, close the chamber, and click OK to proceed with the tests. Here we're doing the basic frequency response at 1/12th octave, again using the bandpass frequency sweep measurement. Next we have the THD measurement, so first at 500 hertz, then 800 hertz, now 1.6 kilohertz, and at 3.2 kilohertz. Next, we measure the high frequency average dBSPL, then the equivalent input noise, then the steady state input output, and next the attack and release. So we're going to step from 55 to 90 dBSPL and back. This is the IEC IMD frequency sweep. Now I have the ANSI sweep also in this project, but I've unchecked it just for the sake of not taking up too much time, and it's very similar, so there's no need to do the two measurements. Next, we go to the signal path where we measure the battery current, 1.28 milliamp. And then we go to the telecoil measurements. So at this prompt, I get a message to place the hearing instrument at the point of maximum magnetic field strength with the microphone in the coupler. So with these telecoils, the loops, you can get the position where the strength is a maximum can vary from box to box, and you're supposed to position the hearing aid at the point of. In this case, I'm just going to leave it where it is. It's close enough for demonstration purposes, but I'm going to switch the hearing instrument to telecoil mode. And I just wanted to point out, if you look at the FFT monitor, you can see, pretty noisy signal, a lot of energy at different frequencies, but watch what happens when I switch on the telecoil. So you can see here, we're getting a lot of noise at very discrete peaks, and those are multiples of the power line frequency because the telecoil is very noisy. So the prompt here says to set the gain to the reference test gain, and it's still at the reference test gain. I'll close the chamber to isolate the system from noise and click OK. And now we're measuring the telecoil frequency response. This is the SPLIV that we talked about during the presentation. And then we have a prompt to set the gain to full on gain. So I'll just change the gain, close the box, click OK to carry on with the tests. And now the system is generating a sequence report. So as you can see here, we have a very nice report. We have a summary of all the measurements. We have the device ID that we entered, 123478. The summary tells us if the system passed provided. And we have the acoustic measurements here, the battery and the telecoil measurements, and the overall result is a pass because everything passed. Here we have the APX instrument ID, so its serial number, the date of calibration, and the version of this. And then a complete description of all of the signal path setup, the output, the sensitivity of the microphone, and so on, and a detailed list of the test results, including all of the graphs. So that's kind of a very quick demonstration. And as I mentioned, these project files are available for download for you to use. And of course, you have the tech note, which you can use to follow along with the project. So at this point, I'm just going to switch back to the presentation and see if we have any questions that people would like answered.
Apologies here, Joe. I'm having some difficulties with my microphone.
Okay. Glad you're still there.
Yeah, I'm still here. Everyone, if you have any questions, there is a chat function in the corner of your screen. Please submit those, and we'd be happy to answer them for you. While we wait for questions, I'd like to take a moment to tell you about some resources that are available to you. If you go to our website, www.ap.com, we have a myriad of audio test assets available, from tech notes to application notes. So be sure to register on ap.com to get access to all of that great information. In addition, you can also check out our blog, ap.com/blog, of which Joe is a regular contributor. So be sure to check out our blog and view information that we have available there. Let's see, Joe, I do not have any questions in the chat. So, ladies and gentlemen, if you have any questions, feel free to reach out to us at our tech support team, techsupport@ap.com, and we would be happy to help you out or answer any other questions you may have as they come to mind. And again, I will be sending a recording of this presentation to you later this week, so keep your eyes peeled for that as well. So Joe, great work. Appreciate your time. And that concludes this webinar.
That's great. Thanks for your help, Paige. Appreciate it.
Thank you. Yep. Take care, everyone.